All right, for this first one, just 1/2 times 6 to the x. We're identifying domain, range, and y-intercept, and asymptote. Okay, so we're thinking graphing. This is just a quick review of that. What is the 6? Like, what's it called? What letter? Maybe you want to use that?
B.
It's B, which is our base, right? So is this growth or decay? This is definitely growth, like really fast growth. Okay? What is the half? That's A. Let me put B right here. So A, and A tells us a couple of things, like what? Yeah, it can contribute to the start value as long as we don't have a k. It's the y-intercept if we don't have a k. Did we write that in your notes? Yeah. So in this case, it is the y-intercept. And the reason why is because if we stick 0 here for x, what is 6 to the 0? 1, and then it's just 1 times a half. Okay, so A tells us that. Also remember it tells us if it reflects. So in this case it doesn't. It does slow it down a little bit, so that would be like what we called and could see better with parabolas and absolute value functions. It would be called a vertical compression. Do you remember that phrase? Okay. It doesn't ask us for that though. Alright, so there's no k. So what is the the asymptote, which is a y equation? 0, yeah. So asymptote is y equals 0. Alright, domain then. Well, if this is a growth function, which it is, let me redraw that one. It's probably better to do it this way. So this thing is going through 1/2. Is it growing faster or slower than the normal parent that we look at? What was it? It's way faster, right? Because the normal we did was 2 to the x. This is 6 to the x. It still does this though, and then it just shoots up faster. So you can't, just on a sketch, you can't really tell that it's different. But I would definitely recommend sketching first before you do domain and range. I just think it helps with those. So now we know that all x values are going to be used. Like there's no restrictions on that. Range does have a restriction. Where does it start? Remember, range is y value, so bottom up. It starts at 0. Okay, we're not going to ever hit 0, but it does start there. So that's why we use a parenthesis. And then it goes to infinity from there. So you need to be able to do something like this on your quiz that's coming up. Perhaps sketch the graph. Maybe identify the transformations if there happen to be like a +7 or something at the end. Like that kind of stuff. How'd that go? That fist to 5 on just that graph stuff. Okay. Alright. Rabbit population was 144,000 in 2016. Guys, on these, it's really important to read the date. Because often in real world context, we're talking about dates, but then we have to use those to find the time frame that we're analyzing. So in this one, it's decreasing. That's an important detail. Of course, our rate as well. So use an exponential decay function to approximate the population. In this case, we have to write our own. I would maybe start with P. Actually, even before that, D. D of T is what we wrote in your notes. What was the format for that on the other side? If you're blank to start, you know at least it's a decay function. So how do we start those off? Huh? I'm saying, what are we going to write over here? We had a canned format that we can apply to these decay functions. Yeah, good. A, what goes in there? 1 minus the rate, and then the time, okay? So that was our canned, like plug and chug, plug and play function. I would change this to a P, because we're talking about P population. But you could also maybe do R if you'd rather. In fact, maybe for people who aren't here, we'll change that to an R. So rabbit population is a function of time. A is what? In this equation, what is A? Yes. Yes, it's the initial value, right? Initial value. So it is 144,000 in this problem. Good. All right, next. 1 minus the rate as a decimal, don't just stick 7.2. So 0.072 in there, and then of course t is just our variable. Right. Probably before I did this problem, I would go ahead and subtract, because it looks nicer than having a 1 minus in there. What's 1 minus 0.072? I don't need that. And we get 0.928. Which one do you guys think looks better? Yeah, it's just less in there, right? It's simpler. All right, and then the question says in 2036. Do I plug 2036 there? Yeah. Okay, so that makes this right here is going to be 20. So our final calculating function looks like, I'm tired of writing it. Looks like that with the 20. So now we need this. 0.928 to the 20. And we get 32,308. 309 if we round. Starting from 144, that's a pretty big decrease, right? If you think of this as people, maybe they're moving out of a region or something, that would be a completely different town after 20 years. If we started with 144,000, that's like Junction Valley. It's a little smaller than Junction. And if we lost that down to 32, that would be crazy. That would be a lot smaller. So probably not as noticeable as rabbits. How'd that go for you? So this is definitely something you'll need to do for this quiz coming up, is write functions and use them to solve problems, okay? And mostly, not mostly, about half of them will be using these two. And maybe we should box those or something and stand them out a little bit better, but template equations is what we call them in the notes. So if it's growth, you can start here. If it's decay, you can start there. Plug in what you know, and then just solve with whatever numbers you're using. Okay? Any questions on those? Let's check your homework, the classwork homework. So number 12 asked you for the y-intercept, which was just looking at a in the function rule, which is the 346,000 number. That was the y-intercept, just the first initial value. Okay, that was 12. Number 24. Here's your function rule. That's really small. So 4,007 times 0.9964 to the x. Basically what we just did in our warm-up. Exact same thing. Plug in the start value, 1 minus the rate to get your decay factor of 0.9964. And then when you plug that in, you get 3,728 as a result. Number 25. Okay, this one is interesting. I want to point it out before we move on. So this word quadruple, we know that means 4, but this is the growth factor, not the rate. In other words, you don't have to add 1 to it. It's like it already has that built in. Okay? So words like doubles, triples, quadruples, those words already have the 1 plus in there. And so you can just dump the 4, as you can see, straight into your function rule. So 50 times 4 to the x. If it was tripling, what would that look like? 3 to the x, right? We don't have to add 1. Good. Once you plug that in, you get 51,200 bacteria. All right, 20 was 26. What was the next one? Okay. So this is a decay function. The initial number of teams in the tournament, that's the answer for B. So 50% or 1/2 is our decay rate. What does it mean by reasonable domain? Let me put this problem up so we can look at it. When it says what so single elimination, this is kind of like what we're doing right now with March Madness, college basketball. This is kind of what it's talking about. So what does reasonable domain mean? Is this, we just did on our warm-up, we did an infinite domain for that graph. Of course, this is decay instead of growth, but it's still, does that make sense? Can we have infinite time? In this case, time? No, so it doesn't make sense. Okay? So when it says reasonable, it's talking about in context, in the story, what does it make sense to limit it to? Like, in this case, teams, rounds is kind of a function of time, but we don't have infinite rounds. You're a basketball guy. How many rounds are in March Madness? Isn't it like 8 or 10? 6 rounds. So that would be a reasonable domain for the March Madness one. Okay? And then same with range. Like this isn't going to shoot from infinity down to nothing. It starts somewhere. For March Madness, it's 64, right? So that would be 64 to 1 team. So, guys, that's all it means. That's a pretty big idea, though. Reasonable domain in the story, what makes sense to say. All right. Any questions on any of those? How'd they go? Those of you who did it. Okay. So again, more problems like what you could see on your quiz, writing function rules and using them to evaluate. Has anybody ever seen a Petri dish? Like put a scrape on there of bacteria and then come back and see it overgrown? It's gross. All right, cool. Grab your note packet. Let's talk about the next thing. You guys know who Warren Buffett is? You ever heard of him? He's one of the wealthiest men in the world. He's old now, like pretty old, but for a long time he was kind of one of the big gurus of billionaires. He's still mega rich. Here's a quote from him. What do you suppose that means? This kind of gives you a clue about some of what we'll talk about in this section. I mean, I don't know what he means by lucky genes, but what do you suppose he means by living in America? How would that contribute to his wealth? Yeah, capitalism. It is indeed that. Do you guys know what compound interest is? Okay. This is something that if you grab onto as a young person, you could be a millionaire by the time you are retired without it being unrealistic at all. And we're going to talk about how. Okay? It's not unrealistic at all. So this section is exponential models. What we're going to talk about is one of the big topics is interest. Interest can be a good thing or a really bad thing, depending who's lending the money. You'll learn a new mathematical constant, which is E, another letter in math, but this one actually represents a number. And we're going to learn about, it's kind of a twist on growth and decay. We'll say it that way, okay? All right, so why don't you grab your calculator and work through this slide. I'm try to just make this just a bit bigger. Here's what's happening. We're doing bacterial growth for now. It says each one is carefully controlled to maintain a specific growth rate. Here's what's going on. Like, you're going to say, well, why are we doing this 4 different times? Okay, so before you start, I want you to take note of how these are different. We're always starting with 10,000 bacteria, so that doesn't change. What does change is the rate of growth and how long we let it grow. And what you're going to explore is how does that affect the final number. Before you do, so can you stop, Lena? Before you get any numbers, do you think a higher growth rate for less time is better than a lower growth rate for more time, or vice versa? That's really what you're going to compare. In other words, which one will create more bacteria in the end? A higher rate, less time, lower rate, more time. I want you to predict. Just in your head, which one do you think is going to create more bacteria? Or are they going to be the same? Because if you notice, all of those multiply to be 8, like the numbers do. Everybody got an idea? Prediction? Okay. If you're ready, go ahead and run the numbers for the final count. Also, do you know how you're plugging it in? Like the 1 plus 0.08 to the 1, right? Like you have to redo that equation each time. I'm going to write those in while you guys are calculating. And then, of course, times 10,000. Should we put that in there as well? First of all, was your prediction right? So 1.08 just for one day, 8%. What was the total there? Blake, will you tell me these numbers?
10,000.
Okay. 4%, so half the percentage of growth, but now we're doing 2 days.
10,816.
Okay. What's the next one?
10,824. 10,828.
Right. So are you surprised by that at all? Doesn't your gut kind of want to say that these should be the same? If it's all of these are multiplying, or at least if we just look at the raw number, 8 times 1, 4 times 2, etc., those are all 8 when we multiply. So why is it different? We end up with 28 more bacteria by doing 1% 8 times instead of 8% once. Yeah.
Because it's growing by a larger percent of the base each time. Like, it'll be 1% of more than 8% of less.
Okay, I followed what you said. Did everybody? Okay. Here's what's happening. What is 1% of 10,000? Remember, with 1%, you just move the decimal place twice to the left. So 1, that was too far. 1, 2. So 1% of 10,000 is 100. Okay. So after 1 day, we have 10,100. But then, this is what Lena was saying. We take 1% of that number, right? Whereas in the 8%, just one time, we're taking 8% of 10,000 only once, and then we don't continue to grow it. Okay, so this now becomes 1% of this number, which is 101, and then we add that on, so then we get 10,201, etc. Okay, so it's growing on the growth. Does that make sense? That's a really big idea. In other words, each time the bacteria grow, now our next round is growing on that new growth, and etc., etc. Okay, now switch your brain over to money. You see how that could be a really good thing? If it's you getting paid the interest, okay? Because then your money that's getting interest is getting more money and more interest on that. All right, what do you think if we did 0.5% for 16 days? So doubled the time, halved the rate one more time. What would we predict to happen to that 10,828? Think it'll go up or down? So let me erase this. 0.5%, 16. It still multiplies to 8. It's just the next phase of this. So 1.005 to the 16. Of course, 10,000 times that. Did you do it? What'd you get?
10,830.
So see, it didn't go up much, but it's still a little bit more. Okay, and of course we could continue that trend, and it would just start going up incrementally smaller, but still would be higher. Okay, this is the idea of interest, and we're going to learn about compounding, which means that's what's going on where we take growth on the growth on the growth. Okay, it's pretty cool stuff. Before we do that, read this problem. Okay, so this problem wants us to find the monthly growth rate if it's 2.5% per year. What does your gut say to do? 2.5% over the whole year. How much per month? What does your gut say? Colin, what does your gut say to you? Divide by 12. Yeah. Okay. Trinity, what about yours? So do you guys agree that it seems like you should just divide it up by 12? You don't, unfortunately. It's frustrating. Okay? What we're going to have to do is write this as a rate, which would be what? If we wrote in our growth factor, what would it be? 1.025. Okay? That's our growth factor. And we're going to take that number instead and take the 12th root of it. You guys ever done a 12th root of something? Okay. So you have two options depending on which calculator you're using. There is a command in there to set up a root where you can pick the root value, in this case the 12th root. But there's also, you can do it as the denominator of a exponent. So 1/12. Those two are equivalent. In fact, that's going to be our next unit. We'll learn some of that. But for this, we need to just be able to do it. So basically, in other words, instead of dividing by 12, which is so close to what we're going to get, but it's not exactly correct, you have to take the root. However many times you're dividing this up into, take that root of it. Okay, so I do want to put this in your notes. So grab that, we'll write it, and then we'll do the problem. And so that you have a reference, we're going to call this exact rates. And put C example. Okay, it's not what you think. Our gut says just divide. You can't. That's not how it works. And the reason why is because this is an exponential, not a multiplication, which I know that's kind of talking out both sides of my mouth. They're kind of the same, but without getting into the details, that's kind of the idea. The prompt will usually say some version of this. So find the exact, and then in between exact and rate, it will say what term you're doing. So in the problem that we just saw, it would say monthly rate, exact monthly. It could say exact quarterly, semi-annual, weekly, daily, like any of those different ones, okay? Let's kind of clarify what's going to happen here. If given, usually you'll be given an annual rate. Guys, what does annual mean? That's for a year, right? How do you, there we go, how do you find the exact partial, think like monthly, weekly, etc. rate? Are you familiar with words like quarterly, semi-annually? Are you familiar with those kind of words? What is quarterly? 3 months. Good. If I said weekly, are you familiar with how many days, or excuse me, how many weeks are in a year? 52 weeks. Okay. Daily, how many days are in a year?
365.
365. Do you want to write that in your notes as a reference, or are we good on it? The only one people usually mess up is weekly. Sometimes they forget 52 because it's not a number you say a lot. And then what about semi-annually? That would be 2 times a year, every 6 months. What if it was bi-monthly? Every 2 months. So there's all these weird ways we talk, right? Okay, so this is the question we're answering. And like I said, it's a little bit more involved, but I'll just show you the quick way. So here's the problem that we'll do. Let's say interest rate is 4.3% APY. This is how it's notated on bank sites. APY is annual percentage yield. You guys bank? You do banking? Or is it just a place to dump your money for now? Yeah, just for safety. Okay. That'll change. So obviously you want to find accounts that have higher interest rates, which isn't sometimes easy to do. So what is the exact weekly rate? That's the question we're going to answer. Our gut would say divide that by 52, but we don't. In fact, let's put that caution. Don't just divide. So what did I say we do?
Take the square root of the partial number.
What does partial number mean?
Like, if it's weekly 52, or if it's monthly 12.
Okay, but not square root. We take the period root, in this case the 52nd root, of our factor, okay? So we'll write that, but good that you're kind of following. Okay, so first step, write the factor. In this case, I didn't say it's growing, but we'll assume that. Now, guys, as we go forward, you're going to have to really know the difference between factors and rates. So factor, growth factor is 1 point what? Actually, for people who aren't here, I'm going to write this a little bit more. Write it out a little bit more. What is 4.3% as a decimal? 0.043. So 1.043. Okay, so we need that factor. Not the rate, we need the factor. Okay, step 2. This is the weird step. Take the, how do I say that? We'll do it mathematically. Take the nth, let me write that better. Okay, so we're taking the nth root of the factor where n is the number of requested periods. In the year. So this one is weekly daily, etc. Okay? So, what root are we taking of this? A 50-second root. Have you ever done that before? 50-second root of 1.043. Is this going to be a big number? Okay. Again, you could write that. I think it's actually easier on a calculator to write it as 1 over 52 as a power. That's how I do it, because I hate going through all the menus and finding the command. So I personally would rather do it that way. But I'll show you both. Word algebra 2 takes a long time to explain. Here's what we're looking at. So I'll show you this fast way first. 1.043, forgot the point. 1.043 to the 1 over 52 power. That's the same thing as math and number 5. Do you see number 5 there? Now, depending on your calculator this way, you have to put in the 52 first. This is why I don't like it. It's one reason. So we want the 52nd root of 1.043. But it's the same. So definitely pick your method, but I think the first one is way faster. Okay? Everybody good on where we got that? Okay, this is the weekly factor still. How do we get the rate from that? Subtract 1, yeah. So, it's going to be lots of zeros if we subtract the 1, right? Just pull that 1 off, 0.0008. I'm going to go write that on here. So this equals 1.0008. And for these kind of problems, it's always going to be that really teeny number. Okay, so last step, just subtract or add, like subtract your 1, like solve for r, in other words. Solve for r, as usual. So this is 1.0008 minus 1, which is 0.0008, which is what percent? 0.08%. Okay, so it's a decent annual rate. Weekly, though, we're way down there. That makes sense. Okay. What do you think of that? In case you think this is not relevant, I actually did it yesterday after I talked to my bank to calculate how much interest I could make if I moved my money to a different account. I actually did this exact thing to figure that out. So it is very relevant. I'll tell you more about that tomorrow to help you out with understanding why.